This session is on momentum, which is in paper 2 and is for combined and triple. Momentum is equal to the mass times the velocity. This is the definition of momentum. P is equal to mv. P stands for momentum, which is measured in kilograms meters per second. M is the mass, which is measured in kilograms, and v is the velocity, measured in meters per second. Momentum is a property of all moving objects, and the most important thing about it is that in any system, the total momentum before an event is equal to the total momentum after an event. An event can be a collision or an explosion. Momentum calculations apply mainly to triple scientists. Combined scientists need to understand that momentum is conserved in collisions and explosions, but triple scientists need to complete all the calculations on it. The following slides have some examples of calculations, and it's made obvious on each slide whether it would apply to triple or combined. It's still worth combined science students going through these to understand the main principles, although they will not have to carry out the full calculations. Here's an example of a railway wagon moving at 5 meters per second and colliding with a stationary, not moving, 1,500 kilogram wagon, and the two wagons move together after the collision. The first question asks you to calculate the momentum of each wagon before the collision. This could be on a combined or a triple paper. It's just calculating the momentum using mass times velocity. So for the first wagon, the 1,000 kilogram railway wagon, it's moving at 5 meters per second. Momentum is equal to mass times velocity, so you just multiply the two together. Make sure you know that the unit is kilogram meters per second, as there's often a mark for this. For the second trolley, it was stationary, but with a mass of 1,500 kilograms. This means that the 1,500 kilograms is multiplied by 0. So overall, the momentum of any object that's not moving is 0. The second part of the question asks you to calculate the total momentum before the collision. So we worked out the momentum of the first railway wagon and the second railway wagon, and all we need to do is add the two together. So this gives us a total of 5,000 kilogram meters per second. This could also be on a combined or a triple paper. The next question asks you what the total momentum is after the collision, and again this could be on a combined or triple paper. We just worked out that the momentum before the collision was 5,000 kilogram meters per second, and we know that the momentum before is equal to the momentum after. So if the momentum before was 5,000 kilogram meters per second, the momentum after will also be 5,000 kilogram meters per second. And now the question moves on to calculating the velocity of the trolley. And only triple science students would be expected to be able to continue with this calculation. So we know that momentum is equal to mass times velocity, and the question tells us that the two wagons move together after the collision. This means that we have to add up their two masses, and we get a total mass of 2,500 kilograms. We also know that the momentum after the collision was 5,000 kilogram meters per second. So we can put these numbers into the equation. 5,000 is equal to 2,500 times the velocity, and now it's quite easy to work out the velocity as 2 meters per second. Another type of collision is one that is head-on, for example these two bumper cars, and this type of question is in combined and triple science. So the two bumper cars crash head-on and stop. Explain why both bumper cars stop after the crash. There isn't a calculation here, it's just working out and explaining why they would come to a stop. So if they come to a stop after the collision, the momentum must be 0 because both cars have stopped. And we know that momentum is conserved in all collisions. So the momentum before the collision must also be 0. And this means that the cars had equal and opposite momentum before the collision. But there are also calculations on explosions, and momentum is again conserved, and this type of calculation would only be in a triple paper. So, for example, a bullet with a mass of 0.03 kilograms leaves a gun at 1,000 meters per second. If the gun's mass is 1.5 kilograms, what's the velocity of recoil of the gun? So the momentum before must be equal to 0, and the momentum after must also be equal to 0. So as the bullet goes off in one direction, the gun must recoil in the other direction to be equal and opposite to that momentum. The momentum of the bullet is equal to mass times velocity, which gives us a value of 30 kilogram meters per second. And this means that after the collision, the momentum of the gun must be minus 30 kilogram meters per second. So we can work out what the velocity of recoil of the gun is, and we get minus 20 meters per second. Notice the negatives because the direction is very important in these calculations. Changes in momentum only occurs on the triple paper, and this equation is on the sheet. When a force acts on an object, a change in momentum occurs. This links back to force equals mass times acceleration. But we know that acceleration is change in velocity divided by time, so we can put this back into that equation to get m v minus u over t. And we can multiply it out so that we can see that the force is the change in momentum divided by the time. This equation, that the force is equal to the change in momentum divided by the time, is very important when we look at car safety features. And it applies particularly to airbags, seat belts, crash mats, cycle helmets, and cushion surfaces for playgrounds. In all of these cases, the time to stop is increased. The change in the momentum stays the same, the force is reduced, and this reduces the chance of injury.